This presentation will be on the development of tougher dental fillings through the use of thiourethane oligomers. First, we begin with the clinical problem of tooth decay. Tooth decay destroys part of the tooth and forms cavities. Cavities are formed when acidic plaque is left to sit on the tooth and eat through the outer layer of enamel. Once this enamel layer has been removed, the plaque then proceeds to destroy the dentin present inside the tooth. 92% of adults have experienced tooth decay at some point in their lives. Risk factors that can lead to tooth decay include the consumption of sugary foods and inadequate brushing and cleaning of the teeth. In the figure on the right, you can see a diagram where several cavities have formed in different parts of the tooth. The solution to this problem is dental fillings. Because teeth are unable to naturally regenerate, these cavities must be filled with another material. Over 175 million dental filling operations occur in the United States each year. The procedure itself, as shown in the diagram on the right, involves first drilling away the decayed tooth, then filling it with a filler material. Previously, fillings were made out of other materials like metals, but modern dental fillings are made out of a composite resin. Unfortunately, no solution comes without its problems. These fillings are often subject to deterioration or fracture from everyday activities like chewing. In the figure on the right is an example of a filling which has undergone fracture. Current resin composite fillings last on average only about 7 years. It is possible for these fillings to be restored, but restoration actually increases the risk of refracture, resulting in numerous visits to the dentist's office. These restorations cost patients both time and money, and an increasing number of restorations only increases this cost. Now, to introduce thiourethane and its chemical structure. Thiourethane is identical to urethane, but with a sulfur in place of the oxygen on the main chain. The double-bonded oxygen has 2 lone pairs, making it ideal for secondary bonding. This promotes cross-linking, which will be discussed in the next slide. Thiourethane contains no ester linkages, meaning that it cannot undergo hydrolysis, and it is not biodegradable. This is important for use in the human mouth, where saliva is continuously present. In the figure on the right, you can see the structure of thiourethane and an example of its secondary bonding. Thiourethane linkages connect molecular chains to form large bulk polymers. These linkages and their strong propensity to undergo secondary bonding results in cross-linking, which has been found to reduce polymerization stress by 15 to 35% and increase fracture toughness by 25 to 85% in dental fillings. Thiourethane is also used in other applications, such as protective coatings for cars and decks, demonstrating that its strengthening capabilities have already been utilized and are just now being extended into the dental world. To implement it into dental fillings, the thiourethane oligomers are added to a composite filling with a centrifugal mixer. In the referenced studies, thiourethane filler solution was added to the monomer matrix at increasing weight fractions to explore its effects. The various testing included thermogravimetric analysis, which monitors weight change at varying temperatures, real-time polymerization kinetics and depth of cure, fracture toughness, and polymerization stress. This polymerization stress, which can be visualized in the graphic in the upper left, describes the stress which acts on the filler adhesive as the polymer is cured. As it polymerizes, the filler undergoes a volume reduction, increasing the adhesive strength necessary to hold the filling to the tooth and prevent gaps from forming. As seen in the graphs on the far right, increasing weight fractions of thiourethane filler led to lower polymerization stresses and increased fracture toughness. As demonstrated in these studies, thiourethane not only outcompeted standard filler, but alternative approaches such as methacrylate silanized filler as well. Thiourethane presents improvement in not only the aforementioned mechanical properties, but degree of conversion for a given rate of polymerization as well, as seen in the figure on the left. These improvements should serve to extend the lifespan of dental fillings, reducing the number of required trips to the dentist and alleviating the cost associated with these visits. While this discovery has not yet been clinically implemented, studies involving the use of thiourethane silanized filler in secondary cavities, cavities that have formed in teeth that have undergone previous filling, are currently in progress. Hopefully, thiourethane can soon be implemented as a standard for dental filling production, helping everybody have a brighter, healthier smile.